The way we teach the class is that, well, I guess the way I learn, when I learn a new subject, I get a new toy or a new piece of software or something, I don't go get out the manual, read the manual cover to cover, and then go play with my toy. I just kind of just rip open the box and just try to do it and see what happens. If I have trouble, then I go back to that manual a little bit later. So that's what I thought we'd do here, is let's just rip open the box and let's just try geometric tolerancing here in Unit 1. So what we're going to do is we're going to look at this indexer plate right here. And the indexer plate is part of an assembly. Now, to really understand geometric tolerancing, you kind of have to know how it fits and how it goes together. So this indexer plate right here, how it works is a round part with a pilot. And what it does is it mounts down on the face. It has this pilot to kind of help keep it centered. And then you notice it would still be free to rotate around. So what there is there's this key here that goes in here. You can see it here, and it keys it into place rotationally. Then when it's keyed in rotationally, then they can put the 3 bolts in to fasten it down. And I think you have that assembly there.
Yeah, I have that assembly right here. You can take a look at it. You see here's the same model here that Scott has. And what I have is I have this little piece that I took the screws out, but that stops the rotation of the part. Here's the piece right here. And you can see how these two parts go together. They're going to fit. They fit down on this face, you see. And then what it is, how is it's located back and forth. It's located by that pilot right there. And then once it goes on, and we were interested in getting these screws inside of the hole, so we're interested in what controls the rotation. And you can see in our assembly what I have is I have this piece here that's on the side, and what that's going to stop is the rotation. So we called it an index plate. So what we're looking at is if we were interested in tolerance, this particular part, this indexing plate, what would we use for datums? How would we set up a datum reference frame? And how would we control the features? So the important thing is how does it work? And what it does is it goes together, it mounts on that face, that sets the attitude, and then you notice back and forth, if you can hear that back and forth, it's locating on that pilot and rotates with that key. And I think you have the drawing there, don't you?
Yeah, here's the drawing. And let's just take a look at a couple of the feature control frames on here. Now we'll start with kind of some of the easy ones here like this one. So what they do is they pull off an extension line off that surface. So they're looking at this feature, this surface. And now what do you want done? This feature, and what symbol is that one there?
Now that's the flatness symbol.
Okay, so they want it to be flat. Now the next one is the shape of the tolerance zone. Now notice how there's no symbol here, so it goes back to that default tolerance zone. Remember that default tolerance zone was a total wide zone or 2 parallel planes. And this tells you how far apart those parallel planes are. So I have this here. So what you're imagining is you're imagining this. 2 parallel planes separated by 1/10 of a millimeter. Now remember what 1/10 of a millimeter was. That was like, a cat whisker I'm trying to stick in there. So you kind of have to use your imagination a little bit. That's up to the quality engineer. They have to come up with a quality dimensional measurement plan that tells you how to check it. And they have to come up with a quick and accurate and a cheap way to do it. And sometimes quick, accurate, and cheap don't always go together. So you kind of have to find that perfect balance of how much money you want to spend and what accuracy is required.
Yeah, because what it does, sometimes it gives geometric tolerancing a bad name. They say we put this geometrics on, everybody gets different answers, nobody can agree. Well, geometric tolerancing doesn't tell you how to check the part, right? It just mathematically defines what the tolerance zone looks like. How you're going to verify that part then, that's what Scott said, you look in a dimensional measurement plan. And maybe because we could have suppliers, if I want to make a flatness check, if you want me to check this for flatness, I just hold it at the light and see if it's shiny, and that's a check, isn't it? That's a way to do it. So what was your procedure? So we're going to talk about dimensional measurement plans a little bit later in a later unit, and I think you'll find that interesting too. We'll talk a little bit more about the verification.
All right, so we've called it flat, and now the next thing we do is we call it Datum Feature A. So Datum Feature A, that's something that we want to measure off of. Now remember though, your parts really don't look like this, and to better explain it, you have to show you what your parts really look like. What they really look like is they look like this. Now this isn't your parts, of course, this is more of like your competitor's parts, but at some degree this is really what they look like. If we zoomed in and we saw the little imperfections, this is what we see. Now what we said is we called that the datum, so we wanted to be measuring off the surface. The problem is, how do you measure off the surface? Look at it, it looks like dirt. How do you measure off of dirt? You have to measure off something perfect. So according to the standard, what you're supposed to do is you're supposed to take a perfect plane, and a perfect plane that contacts on the high points, that is what we call our datum A. Our datum A is going to be the perfect plane that contacts on the high points. So in this view, what you get is you get a plane in this view also. that you can measure off in and out of the paper. Now, you see that ugly looking surface there? That also has a name, and what they call that is they call that the datum feature. So there's kind of two things here. There's the datum, and then there's the datum feature, and you have to recognize the datum is the perfect plane, the datum feature is the ugly looking surface. Now, what's the difference between those two?
Oh, that would be your flatness tolerance.
So that's their flatness. The flatness is what we call qualifies the datum feature and makes sure that your datum feature is good, even though our datum, your datum feature is good relative to your datum plane. What you do is you take a cylinder that is related to datum A, and that cylinder right there, when you collapse it on there, that's what you're going to get this axis. So we need to make sure that our coordinate system is 90 degrees, so you're measuring from the center of the tolerance zone from the related cylinder, is what they call it.
You notice what Scott's doing here is we're taking the imperfect data. We have the imperfect part, and what we're trying to do is take perfect geometry and put it on, because perfect geometry is what we think of. And we can't work with this thing, you know, parts that look like a potato and stuff. We have to go and put perfect geometry back on. So that's what the geometric tolerancing is doing, is matching perfect geometry to imperfect geometry, because then we can measure from this perfect geometry.
Mm-hmm.
So probably what they would do then is that they would take their part, put it on here, and once they put it up against that face, then what they're going to do is that they would turn it up like this. When they turn it up like this, probably what they would do is level that face out. So they would come across here with their indicator, and once they level that surface out to make sure that it was level, so they got their flatness tolerance. Now once they have their flatness tolerance, now when they take the part, they can take it, put it down here, you notice, and now we're going to level it out at that bottom surface. See how that bottom surface is leveling it? And now what they have the part and they clamp it on. Now when they take any measurements here, they're going to be coming from the center of that pin. Up and down, they come from the center of the pin, the part is oriented, and they can make all their measurements up and down. And now when they want to make measurements in the other direction, you know, back and forth, then they just rotate 90 degrees and then they can make their measurements in the other direction. If they need to make measurements up and down, you see what they're going to do? They're going to take them and they're going to measure the thing, so it's in this way. They're going to measure it, you know, then they can measure from the surface plate and go this way. Or from this here, this would be their datum. So what it is it's a complete coordinate system. You see there's a different coordinate system, X, Y, and Z. So this is an open setup. If they were checking this part with a coordinate measuring machine, it clearly defines what they're supposed to do. What it's telling them, first of all, that what they want to do is they want to establish a plane on this surface, right? And once they establish that plane, it's not going to come into a perfect plane when they touch more. How big is that zone? That's going to give them their flatness. Then they have to find the center of this pin. And the way the coordinate measuring machine works is that how many points you have to need to find the center.
So what you've seen here is on this print is you've seen just the geometric tolerancing applied in orthographic views. What a lot of companies are doing is applying more and more geometric tolerancing. Now let me show you another concept that actually some other companies are starting to use. They're starting to use this other standard called the Y1441. And what that is it's digital product definition data practices. And what it is, it shows you how to apply geometric tolerancing to models, to CAD models. And that's what some companies are starting to do. They say, why are we making all these paper drawings when we have the models that can tell us all the information we need? So what you do is you point to that surface and you say, in the model, I want that to be flat and I want it to be A. This over here, I want that to be B, need it perpendicular, that's C, and it needs to be profiled. And these holes need to be positioned within 0.4 to ABC. And all the basic dimensions and all the CAD definition is all in that model right there. So there's really no need for a paper drawing on this one.
Yeah, and it's kind of nice when you look at it. It's exactly what we said. You notice what that drawing is doing is it takes the model just like we have said all along.